Good evening, students. We're going to start physics paper 2, and I'm starting with the question 1. So question 1 is basically based on finding basically finding a drift velocity in a conductor. As we can say that the metal wire, a lot of information is given in the question. Let me say cross section area of a conductor is given is like a 0.5 times of millimeter square, 0.5 times of 10 raised to minus 6 meter square. Let me convert it to SI unit. Yeah, and the length of the conductor is given as 100 meters, and battery of EMF 2 volt, and its internal resistance is given as 1 ohm. And yeah, there is a wire is given, as we know that. And what is the resistance of the wire? It is rho L upon A. We are very aware of that. Rho stands for the resistance, but the question given is in the form of a conductivity. So inverse of that, L divided by sigma times of A. If I substitute the values of all the values over here, the conductivity value provided, how much is that? Conductivity of the wire is 6.35 times 10 raised to 3. Conductivity. Next, if I substitute all the values, 100 upon 6.35 into 10 raised to 3 into cross section area, 0.5 times of 10 raised to minus 6, that sums up to 1 ohm. That's equals to 1 ohm. Now let us find what is the current through the conductor. Electric current through the conductor from Ohm's law, we can say that V upon R, R plus R, internal resistance must be considered, and EMF is given as, I have mentioned it as a E, and 2 upon 1 plus 1, and that adds up to 1 ampere. Yes. Now we are becoming closer to the answer. We need the drift velocity of the electrons that are passing inside the conductor. And how can we do that? We know that I is equals to N times of E A V suffix D. So here N represents number of electrons per volume, and E is the charge of electron, and A is the cross section area, and VD is the drift velocity. Now how are we going to find first? Let me find the number density. N can be written as number density, number of atoms present in a conductor divided by the volume of the conductor. And once again, the number of electrons present inside the conductor can be represented as, it depends on the mole value. We are given the number of moles also. Now I can write this one, N is equals to mass of the conductor divided by the mass divided by molecular mass multiplied by Avogadro number times divided by volume. Once again, N is equals to, mass can be represented as here density into volume, density rho into volume V times of capital M and Avogadro number A again upon volume gets cancelled. So the number density, number of electrons present per unit volume, can be represented as density times upon molecular mass into Avogadro number, which gives rise to, if I substitute the value, which gives rise to total, it sums up to 6 times of 10 raised to 28. 6 times of 10 raised to 28. Now the actual question is to find the drift velocity, and the drift velocity is current I divided by number density, charge of electron, into the cross section area. And if I substitute all that value, we come to know the current is 1 ampere divided by number density is 6 into 10 raised to 28, charge of electron 1.6 into 10 raised to minus 18 minus 19 into cross section area 0.5 into 10 raised to minus 6. Yes. And what does it add up to? Drift velocity which adds up to approximately 0.208 times 10 raised to minus 3 meter upon second. Now, but the question was asking in terms of millimeter per second. Now 10 raised to minus 3 meters become millimeter, 0.208 millimeter per second. Yes, and we can conclude from that this is option C is matching for that. Right. Now we'll see the second question. Okay? We'll see question number 2. And what is it asking for? A nuclear reactor starts producing a radioactive nuclei X from time t is equal to 0 at a constant rate of alpha per second. So production rate is given here. Production rate is alpha. And each decay of X produces energy of E naught. So in each decay, energy in each decay is E naught. Now, which is utilized to heat a liquid of mass M, and specific heat of liquid is given as S, assuming no heat loss from the liquid. And so there is no loss in the sense that whatever the energy is released in the reaction totally converted into heat energy to raise the temperature of the body continuously. And taking lambda as the decay constant of X, the rate of increase in the temperature of the liquid. As the question is concluding that there is no losses of energy, the liquid is continuously gaining the energy coming from the reaction, so temperature must be increasing continuously. And now at what rate is it increasing? That is the question for us. Now first let us see the rate of change of number of nucleus. The rate of change of number of nuclei. We can say that it is a production rate minus the rate of decay. So how many X elements are being producing, and in that produced X elements it's been decaying into some other way. By that energy is liberated and absorbed by the water. Now this is number of nuclei decaying per second is given as production rate is given as alpha minus, and decay rate is, we can represent decay constant multiplied by the number of nucleus present at that instant. Now let us do the math. dn upon lambda alpha minus lambda n is to dt. Let me take the integral part of it, and what does it sums up to? And okay, let me take the limits over here. Number of nucleons are changing, produced number of nucleons are produced per second would be 0 to n from time 0 to t. Now ln of alpha minus lambda times of n divided by minus lambda 0 to n, that is equal to t. Now if I substitute the limits, I would be getting, let me send minus lambda to the other side, and this would give rise to me, if I substitute the limits, lambda alpha minus lambda n upon lambda, and that is equals to minus lambda times of t, and 1 minus lambda n by alpha tends to e to the power minus lambda times of t, and 1 lambda n by alpha is equals to e to the power 1 minus e to the power minus lambda times of t. And we need number of nucleons are present at that instant, and what's happening here, alpha by lambda times of 1 minus e to the power minus lambda t, and n is the number of nucleons present at the instant of time t, at that instant of time t. Now but what is the question he been asking here is like the rate of rise in temperature, the rate of rise in temperature. And how do we do that? Can I erase? Yeah. So let me take a space over here from this side. the rate of energy liberated or heat energy. Heat energy produced. It's a dq by dt. That is equals to, it can be dk. Rate of decay multiplied by the energy liberated. R is the rate of decay. Okay, let me say. The rate of decay, R can be represented lambda times of N. Now, if I can substitute and the heat energy, Q can be represented as MST. Now, if I substitute all the values into the given equation, I can write d by dt times of m times of s into capital T is equals to lambda times of n into E naught. Furthermore, lambda times of n value we have derived over here, 1 minus e to the power minus lambda times of t into E naught. Lambda that get cancelled out, but we are interested only in finding the rate of rise in the temperature. So d capital T by d small t, and capital T by d times of small t. So mass multiplied by specific heat, if I am sending on the other side, lambda E naught divided by m times of s into 1 minus e to the power minus lambda times of t. Yes, this is our required answer, and this one is option A, first option we got. Thank you.
So look at the question number 5. Question number 3. The question says, a beam of polychromatic light passes through a prism. Okay, thin prism. So they gave a thin prism. So we know the formula for thin prism, right? So the minimum deviation for thin prism is given by mu minus 1 into A. Okay, and then they have also given you the condition for the refractive index, which is varying with the wavelength, which is like n of lambda is equal to alpha into lambda plus beta by lambda square. Okay, so we are supposed to find what is the d minimum for corresponding lambda minimum. Okay, so when do you get d minimum? So we are supposed to find lambda minimum. So how do you find lambda minimum? So they give you refractive index is minimum, so you can find that. So d by d lambda of n of lambda will be equal to 0. Okay, so for the refractive index to be minimum, you know the condition for maxima and minima, right? So we just use that. Okay, so now you differentiate this, you will be getting alpha plus, this is like beta into minus 2 divided into lambda power minus 3, which is equal to 0. So this, if you solve, you can find you will get 2 beta divided by lambda cube equals alpha, right? So from this you solve for lambda. So I'll just write the answer. So this will be, upon substituting, you will be getting like 2b by alpha whole power 1 by 3. So put the values of beta. It's like 2 into 0.096 divided by 3 whole power 1 by 3. Okay, so this will be giving you a lambda minimum. Okay, so how much is a lambda minimum? So this turns out to be equal to 0.4. Okay, so now once you get lambda minimum, you can put that lambda minimum in this equation. Okay, so corresponding lambda minimum will be giving you the minimum refractive index, and then this relation now can be rewritten as, so d minimum is equal to, what is my mu minimum? So in the place of lambda I can write lambda minimum. So what is my mu value? It will be alpha into lambda minimum plus beta by lambda minimum square, okay, minus 1 into angle of prism. Okay, now we have found how much is the lambda minimum for the corresponding minimum refractive index. So just put the numbers over here. So we know the values of alpha. So it is given to be 0.3 into 0.5. Alpha value is given to be 3. So this will be 3 into 0.4 plus beta value is given to be 0.096, right? So 0.096 divided by, and lambda minimum we have found 0.4. 0.4 square is 0.16 minus 1 into angle of prism is thin prism, right? So it is given to be 6 degrees. Okay, so now you can see, just put the substitute it, and then you can solve for. So 3 into 0.4 is 1.2, plus this turns out to be 0.6 minus 1. Okay. Yes. So this is into 6 degrees. So 1.2 minus 1 is 0.2. 0.2 plus 0.6 is 0.8. 0.8 into 6 degrees, so which is equal to 4.8 degrees, which is our option B. Okay. So this is how you do the question number 3. Thank you.
Question number 4, and I hope question number 4 is pretty interesting, and we'll see how it goes. We have a particle of mass m with angular momentum small l is moving in a circular orbit of radius r0 under the influence of an attractive force which is given by vector f minus k by r squared r cap, keeping its angular momentum unchanged if the particle is displaced radially by a small distance dr, much smaller than r0, due to which its radial distance varies periodically, it seems. Now the question is the corresponding time period, that variation of radial distance, right? Its corresponding time period is what they are asking. Okay, so it's pretty good problem, and it involves the ideas of Newton's laws of motion, circular motion, and little bit of approximations. So let's try and solve this. Okay, so we have this idea that if there is a particle which is moving in a circular orbit of radius r0, let's say this particle has mass m and this is moving with certain velocity. If it is moving with certain velocity, definitely we can say that it has some angular momentum around this path, right? So angular momentum is given, L is given, that's the given symbol. So it is m, v and r0. This would be the angular momentum. But what we'll do is we'll just write this as m times velocity as omega, the angular speed with which it is moving in this circular path, omega r, so the radius is r0, right? So we'll write it as L equals m omega r0 squared. Let's keep this one as first equation. Okay. Now we know that if this is maintaining the circular path, there is a force, and according to our given logic, this force F, right, that is given as K by R squared. It is in the radially inward direction. Since radially inward direction, we are showing in the diagram, no need to write here. And this force is helping it to move in a circular path, right? So K by R squared should manifest as centripetal force. So m omega squared R would be the centripetal force, correct? Now once we get this logic, we'll just see that if this is the given configuration, then K by R0 squared is equal to m omega squared R0. That would be the initial condition. Let's keep that one as equation 2, because this is our initial condition. It was moving peacefully like this with R0 radius and it was maintaining that circular path. So from this configuration, we are going to disturb it. Okay, we'll give a small displacement dr in a radial direction, let's say, and that dr is going to be really small. According to the question, the dr is much smaller than r0. Okay, so we are going to use that and see what changes can happen. Suppose if we write here the small dr here, meaning from here to here we are displacing, and now it is going to move in a bigger radius like this. But according to the given configuration, they are saying that this radial distance is going to change periodically. So we'll see like what happens here. Now because of this increment, right, so this changes in the length is dr. So let's see like what will be the new force. The new force would be K by R plus dr the whole square. This is a new force. This will be the new force. But this new force, if I name this one as say inward force, let me now call that one as F dash. F dash would be the inward force. Okay. Suppose if this is inward force F dash, we could have said this F dash acting like centripetal force if it is just maintaining the circular path. But we also know this, it is not just maintaining the circular path, it is moving, say, from its original position, it is going in a wobbling type of motion where it is just increasing the radius, decreasing the radius. That's how it is moving, right? So because of that, we can't say that this force is exactly equal to centripetal force, because we would have said this way: this is equal to m nu omega square times of r plus dr. We would have written this if it is moving in a circular path, right? But it's given that it is not going to maintain new circular path, right? It is going to change the radius. We cannot make this as equal. So if we write it as equal, it is going to be wrong. So we'll say like, okay, so this is not equal. It will be some difference. So it won't be exactly cancelling up. So there will be a net force here. There will be a net unbalanced force here. So this force minus this force would be some net force. Got it? So meaning you have displaced it with R increased, right? So this minus this would be the net force acting on our system. Now we'll see what will happen with that. Okay. Now with this logic in place, we can write the net force being equal to, I'll just do a little bit of simplification and call this small r as R naught. This is R naught, right? So we can just change this as K by R naught squared, and I lift this one and write it as 1 plus dr by r whole squared. Okay, dr by r whole squared minus, we have m omega dash. So omega dash is a new value of angular speed, right? So we can write that one as omega plus d omega. If there are any changes in omega, we are going to witness that squared times of r plus dr. So I hope you can easily observe this, r plus dr. That is what we have as an equation, correct? Now we have to little bit handle like what happens with d omega. We have small l, which is given as m v r naught, which is m omega r naught squared. From this we can see that changes happening to angular momentum is 0, because from the given data angular momentum we have to keep it constant. So we'll keep that as constant and we'll differentiate it. So that would be 0, and we'll see that variation in L in terms of omega and r naught. So this goes as omega 2r dr plus r square d omega. This is what we have. Then we will just simplify this. So see here, wherever we have r, right, I'll write it as r naught. Just for convention, we stick to r naught configuration. So dl is this. So dl is 0. So we can solve for, say, d omega. So omega 2r dr being equal to r square d omega. So negative sign here. So d omega would be equal to, see, we are just seeing the changes happening to the omega. The changes happening to the omega is given as minus 2 omega by r dr. Minus 2 omega by r dr. Just cancel omega, sorry, r and r, and just rearrangement, you will get this. D omega is this value. So let's plug this information here and let's check what happens to our expression. So here k by r naught squared and 1 plus dr by r whole power 2 minus m omega plus, in place of d omega, right, I'll be writing this one. So omega minus of 2 omega by r dr, the whole square into r plus dr. This is what we will have. Please check once. After this, a little bit of simplification again. So we have net force here, which is k by r naught squared. We'll write it as 1 plus dr by r naught whole squared minus m omega squared. Here I am taking omega outside. I'll simplify this. So 1 minus 2 by r dr, we'll have 1 minus 2 by r dr whole power 2 into r plus dr. That's our equation, right? Now observe, once you are done with this, see, till now we did not do any approximations. We did not use this particular condition yet, right? Now we are going to employ this here. I'll be just ensuring that wherever we have r, it is r naught, right? Because about r naught you are giving a small displacement. So this is what we have. So this is given. here we have this kind of terms, so we'll be using binomial approximation, okay, and simplify this a bit, okay. So as we do this, I'll be erasing this a bit here and rewrite this, okay. So here I'll keep this value as it is because I might need it, right? So I'll just keep this value, and L equals m omega r naught square. I'll write L equals m omega r naught square here. Let's simplify this further. So I'll just take some space here. We know that this is a diagram for us. Yeah. Now using that F net expression, F net is given as, say, k by r naught square. Using binomial approximation to become 1 plus 2 times of dr by r naught. Then we have minus m omega squared times 1 minus 4 times of dr by r naught. Then we'll have r naught plus dr. This is it here. So I think till this point you should be careful. From here on, this mathematical manipulation, you will get it, okay. So from this point we'll have, say, when you multiply this, right, we'll have k by r naught squared plus 2k by r naught cube here, dr here, minus m omega squared r naught, m omega squared r naught, then m omega squared plus into dr, right? So that I will write m omega squared dr. And when you observe this term, we have 4 times dr by r naught. So we'll write, if you observe, when you multiply dr with dr, so dr square, right, will be negligible, and dr by r naught we are considering. So dr squared by r naught is tending to 0. So since we are already using approximation, dr by r naught itself is small. When you have dr square, it is really small. So we are going to ignore that and make it as 0. Okay. So that is what we have. So once we have this, we'll see, like, is there anything to cancel? So we'll have k by r naught squared. This term is same as m omega squared r naught. So this and this getting cancelled out from equation 2. So we have used this equation already now in our system. Now we'll have net force given as 2k by r naught cube minus m omega squared times dr. This is what we have. Now after this, from this we also know this, the net force, right, it is acting more like a restoring force in its nature. So we can write this one as negative of mass times acceleration. This minus just implies that it is like restoring in its nature, right? So we can write this as 2k, same value, 2k by r naught squared, r naught cube minus m omega squared dr, right? So this is what we have. So I'll be sending this mass here to the denominator here, m here and one more m here. So this is gone. So we have acceleration is this value. Let's simplify it further. So we have this quantity. Now you can see that in our options there is nothing like this, right? Meaning you have to be in a position to rethink about expressing in a given terms. So since it's not directly evident, so we'll do a little bit of arrangement. So we had this expression k by r naught squared, right? That is equal to m omega squared r naught. This we already derived it. So from this, and L is equal to m omega squared r, right? M omega r naught squared, because m the r, then we write it as m omega r naught squared. Using these two, we can write k in terms of L. K is equal to L squared by m r naught. K is equal to L squared by m r naught. So use this here and you can express this idea. Omega is equal to L by m r naught squared. Here omega squared we'll have. Just simplify this. Just plug this information here. in place of omega, L by m r naught squared here and square that. Okay, and wherever we have k, we'll substitute L squared by m r naught and simplify. As we do that, we'll get acceleration is given by L squared by m squared r naught power 4. L squared m squared r naught power 4 dr. This is what we will get here. Okay, so once we have this entire thing, right, now it is a condition for SHM. There's a condition for SHM. I hope you know that acceleration and small displacement, this part is frequency getting squared. So I'll be erasing that part. We'll write this way. We have acceleration equals frequency, SHM frequency, square times of dr negative. Correct? So SHM frequency, right? That is given as L by m r naught squared. L by m r naught squared. Please check once. So here we have L by m r naught squared whole square. That is SHM frequency squared. So we'll have SHM frequency as L by m r naught squared. Now time period of that so-called repeated motion, the variation in the radius, right? That is given by 2 pi by that SHM frequency. It will set that periodicity, right? So time period will be 2 pi by SHM frequency would be L by m r naught squared. So m r naught squared. This is what we have. L by 2 pi by L m r naught squared. But if you see that options are not in terms of that, so we have to get rid of r naught and express in a different format. So we know that from this r naught can be written as L squared by mk, right? L squared by mk. R naught can be written as L squared by mk, and if you do that, you will get time period is equal to 2 pi L cube, because when you substitute R naught here, you will have L power 4, one of the L is here, so that will cancel and you will get L cube here, and when you are squaring it, there will be m squared here, and there is one m in the numerator, so there is one m here, and k squared. So there we have. So if you look at the options, 2 pi L cube by mk squared, 2 pi L cube by mk squared, that's our first option, right? So our first option, that would be the correct for this particular question. So everyone, I hope you understood this one. So you can just check out, we have used all these ideas which involves NLM and the ideas of SHM and little bit of approximations. So these are the concepts involved in this problem here.